And I'm very happy I learned something today. I did not know what Monaco was about, so thank you. I'd like to talk today about scientific systems for scientific discovery in the era that we are entering. And of course, as part of our discussion is about this project that Kasana-san and Sana-san talked about, which is with FugakuNEXT. First, I want to emphasize that supercomputing as a community and as a technology interaction point has actually been very key in the history of NVIDIA. Technologies that have come in part from interactions with supercomputing and supercomputing centers can be seen across our portfolio. Many of those technologies are today being deployed at massive scale, also in the build-out of AI infrastructure. Even just a few examples around immersion cooling, the SXM module, both related to work actually with supercomputing centers in Japan. High bandwidth memory was first deployed in the Pascal GPU, which was the part used in the PISDE system in Switzerland. Grace Hopper and the high bandwidth C2C, and bringing ARM to our environment was with Venado in the United States. C2C NVLink is part of the Summit and Sierra systems in 2016 with IBM. So all of these capabilities were things that were developed in part because we worked with supercomputing centers. This is the context of why we're here today, right? We're not here we don't see projects like FugakuNEXT as an opportunity to sell a few GPUs. That's not why we're here. Just to call out specifically, we've spent many years partnering with the Japanese ecosystem across the board, many universities, many centers, and of course, many people that perhaps you might find familiar. So in supercomputing centers today, things are changing. The way that supercomputing centers and their users are solving problems has transformed in recent years. It's no longer just simulations, and then you run another simulation, and then you run another simulation. It's these complex interactions between simulating the reality and using AI to make sense of or pre-process or work with that reality through learning. Many examples of this in recent years, just in the last few years. Gordon Bell Prize winners in weather and in seismology, the work that was pointed out earlier by the other speakers around astrophysics and using surrogate models to model the universe at RIKEN. But it's gone beyond just academic research. It's also impacting what's happening in industry, looking at chip manufacturing and applying AI methods to those types of designs as well. All of these things are being driven from the science side. They see the opportunity of applying new techniques, AI techniques, to science, and they're taking advantage of them in ways that are very exciting. But you don't have to take my word for it. If you were here during Matsuoka Sensei's talk, you saw many examples of how RIKEN and associated researchers are doing a lot of work in that environment as well. And for FugakuNEXT, the system in particular, it is stated quite clearly by multiple of us that the project goals is really about accomplishing science faster. It's not about more flops. It's not about just more bandwidth. It's about getting to new discovery at a higher rate. Called out specifically in many cases as a multiplier of productivity, directly attributable to the use of new AI methods in these cases. I'd like to go through one example of this kind of an application. The reason I want to show it is to kind of walk through what that might look like, because we're tasked with trying to design a system for this purpose. And so we'd like to understand what we're trying to solve. I think most people in the supercomputing world are quite familiar with numerical weather prediction, right? We're taking a state, we have a spatial grid, and we have conditions, a number of numerical parameters describing the state of the area. And then there's a function, a physics function that's repeatedly calculated in sort of a forward time direction, trying to understand what will happen next based on what the conditions are right now. This is a system that means we need a lot of different forward-looking options, right? As everyone knows, weather can be somewhat unpredictable, in part because we don't have the list of every single parameter that may be influencing it. And so this is a combination of simulation of physics and some statistical methods to make sure that we are making sense of the high likelihood probabilities of what will happen in the end. This is an extremely computationally intensive task, and in fact, the weather HPC market is one that's in fact sustained entire companies for many years. But what's interesting is this is changing. The way that this is being approached is starting to change. But just to look at this from a systems perspective, if I'm administering an HPC system for weather, this is what I see. I see a simulation running, WRF or some similar application. It's, a high precision simulation calculation, something we're all familiar with. I give it some inputs, it does the calculation, out comes a forecast, right? Maybe if I'm lucky, I get a pretty picture out of it. And then we just repeat this. Most of these weather sites would do this maybe 2 or 3 times a day. They have actual sort of like hard real-time limits on these simulations because, of course, a forecast that takes too long to calculate is no longer a forecast. And so, this operation happens daily in production. What's changing is new methods are coming online to solve or enhance this operation in a way that is both bringing new capabilities, but also bringing immense amounts of performance benefit. So you could say we start with simulation data, and maybe we have outputs from all that simulation. But the next thing I might do is train a model. Take all of that data and educate a neural network about what simulation data says about past events, future events, and the relationships between them. You can then take that model and run inference about it against it in a couple of different directions. One is you might use something like ForecastNet to do timescale forward-looking projections here's my current state, what do we think the next state will be? We can also do things like CORDIF, which is a weather downscaling or enhancing model, which takes a very coarse-grained, low resolution prediction, and it can actually do a higher resolution, generate a higher resolution version of that same prediction based on relationships in that data. Both of these models have been produced and have been around now for a year or two. And what we're seeing from a results standpoint is these models and ones similar to them being developed by the weather centers around the world are actually as accurate, just about, as anything that comes out of an actual simulation flow. However, what's interesting perhaps most is you could get a ForecastNet result. Here's my initial conditions, what's my new prediction, in about a half a second in a single GPU. The inference is almost instantaneous. Relative to running an entire simulation, using AI, when you have the data to train these models, is an incredibly advantageous performance. Now, there's other parts you can do with this. You can take that inference loop and you can visualize it in something like a digital twin. In Earth 2, in our example, in Omniverse. You could also enhance it over time with new data coming in from the edge, from instruments. So instrument data comes in, we get new data, we feed it into those models and use those to infer again the next step. Many of the applications you might have on your phone that do, for example, nowcasting or hyper-local weather are based on technology like this. It's done individual versions, it's done very quickly, and it's done up to date with whatever the most latest data is. Very cool technology, but I ask myself as a systems person, what does this look like? And it's not like that simulation where I just ran a simulation and I was done. This is a flow. And by the way, this flow might be managed by an AI agent on the side, moving the data around, generating new things, sending off requests, training new models. These performance requirements of these different workflow components may be drastically different. They are drastically different. And so we have to think about that a little bit. So for example, WRF simulation, as I mentioned, FP64, FP32, heavily vector compute. You can use a fairly standard scale-out HPC architecture that we're all familiar with. But the model training part of this, we want more tensor compute. We need a mixture of topologies depending on what the model looks like. And the precision usually for training these models is now moved down somewhat to something like an FP16. Similarly, on inference, we're going to be inferring in a lower precision. Usually it's a result precision, roughly what your answer is in. And it might be, for example, some sort of high bandwidth scale-up pod, depending on the size of the model and how it interacts, what the model architecture might be. You might have to do some graphics if you're doing digital twins, and you might have to have a way to interact with that. We have edge instruments. We have to have high bandwidth data streams coming in from the outside, long-haul networking, and protocol support to make sure that that data stream coming in gets access to the compute resources that are needed to catch it in perhaps even real time. And then, of course, over here, our agent on the outside might just need very low precision language models, FP4, and some high bandwidth scale-up pods. How do we design a supercomputing system for this? It's not ramp up the floating point 64 or the 32 or the 16. It's all of them, but how much for each? Do I care about memory? What's the network topology? The answer is much more complicated than it's been in the past. So if we're going to do a design for this, the first thing we have to figure out is not the hardware components we have to work with, it's what's the software doing. And so at NVIDIA, for example, we spend a lot of effort in developing libraries for different domains. These are our CUDA-X libraries. I think as of today, there are over 350 of them. They're each focused on different verticals or algorithm types, not to solve every problem in our own software, but to investigate and probe these different domains and find out what is it they need, what software do we need to write, what algorithms do they use, and learn from that. It helps us build highly optimized hardware-software co-design in each of these verticals because we are able to look at both and give feedback in both directions, right? Hey, maybe you should try this new algorithm based on new hardware. Hey, maybe you should try this new hardware idea based on the algorithmic benefit we see. Those kinds of conversations can happen inside a loop like that quite easily. It's not just libraries, right? Now we're seeing this same thing with models. The models available are diversifying all over the place. We have models, obviously many language models, but we also have biomedical models. We have earth science models, weather models, climate models, physics models for aircraft wings, autonomous vehicle models for control and driving and analysis of its surroundings, robotics models for humanoid robotics. All these types of models are diversifying, and so we need to have manipulated and worked with them to understand how they might be used, and how they might impact a system. From an NVIDIA standpoint, we are working very hard to make lots of open source models. We want the community to be able to develop models based off of ours, use the tooling, refine them so that they don't all have to start from scratch. So something to keep an eye out for. But the most important thing is, yes, we want to develop software. Yes, we want to develop models. But most of the time, that isn't enough. You need to have somebody that cares about getting a real result out of it. You need to have a point of place that cares about it. And so that's where we need to bring in partners. And in particular, we are partnering quite closely with RIKEN, yes, on FugakuNEXT, but beyond that, looking at things like quantum and HPC hybrid and AI for science. There are 2 different systems projects that are being installed now based on our Blackwell architecture for the purpose of collaborating on these types of technologies. So excited, again, to continue to do that. So if we're designing hardware, we start from the software, try to understand what it's doing, and then we have to look at the hardware side. And if you look at what modern systems, HPC and AI systems, look like, there are a lot of components. On the bottom of this slide are 7 chips. And that's actually just a subset. And we're revving most of those chips pretty much every generation, every year or 2. And all of them have impacts, right? What network do I need? Do I have features I need in the network? How does that interact with the GPU I'm using and what that memory performance is or what the CPU is, right? You have to digest all of this to do a full system-level code design. Again, system complexity is accelerating. And so if we need to be able to digest and make sense of how to put these things together, one thing we also want to do here is find partners, find people to work with that have expertise, that know direction, and can help us explore together. And one very good example of that is Fujitsu. Fujitsu has been building CPUs and CPUs for HPC purposes for a long time. The FugakuNEXT, the prior systems, Fugaku, the K computer, were incredibly reliable. They had lifetimes where they produced useful science for a very long time. And both of those are characteristics that lead us to believe we might have something to learn from them. So we wanted to partner with Fujitsu, and we wanted to make sure that we integrate our ecosystems together. So Fujitsu is the lead candidate, the lead partner for the NVLink Fusion ecosystem, which is our attempt at NVIDIA to allow others to bring their ideas and their value into our giant stack of hardware and software. So we're excited to be on this journey together, and we're working together to make this integration as good as it can be. But at a system level, again, the complexity doesn't stop at hardware. It moves on to software. And I think many of you have seen charts like this showing how performance of components of GPUs, in this case, our GPUs, has evolved over the years. And these go, in the bars from gray to orange to all the way to green, from the Volta GPU all the way to the Rubin GPU that we just announced a couple of weeks ago. And what you can see is, from a performance perspective, as we have evolved over the years, the ramp up of precision is it's going up, but it is going up immensely fast at the bottom end. That's driven by 2 things. Everybody says, well, it's driven by the AI market because the AI market is buying a lot of GPUs. That's not wrong, but it's actually not the technical reason. The technical reason is twofold. One is they have ideas, models that happen to be tolerant to low precision and can get performance benefit. And the performance benefit is because smaller precision is much simpler to implement in hardware. And so if something can use that, and we can then build it easier, that is a sort of a win-win for everybody, right? We can make the numbers go up easily, and they can take advantage of it, right? So this trajectory has been going on for a long time. But one question is, of course, this is an immense amount of resources across the board, across all these precisions for developers to have at their disposal. But how is it, how can we make some of this gigantic growth in the right of this chart available to more than just a few users? Can we make it more broadly applicable? Can we use that hardware in other ways? And so we're doing a lot of efforts around mixed precision computing. There's really three pieces of mixed precision that need to be pursued. One is, of course, you have to have hardware that supports mixed precision, which we obviously do. The second one is we need to have algorithms, right? If we are using mixed precision computing, we need to understand the numerical properties of the calculations we're trying to do and of algorithms that take advantage of mixed precision but still give us the result we need from a numerical perspective. And the third one is we need developer tools. We need ways for developers to understand the middle part. What precision should I be using? What is my application? What would it tolerate? And so you can see examples here like an analysis, and I believe this is from the Raptor paper, of an application looking at how many mantis bits does it really need in its calculations and where does it fall off of an error threshold. There is a lot of work on this in the community. This is sort of let's call it a virtual desktop of our numerical libraries director of papers that are very prominent in what we're thinking about these days, looking at things like emulation, mixed precision, use of things, as well as analysis. I will point out quite clearly that many of these papers have authors from Japan. Japan is an excellent source and an excellent leader in understanding the numerics of computing and the performance of those patterns. And there are real benefits to be had here, right? Just looking at a mixed precision iterative refinement kernel, right, which is really a mixture of doing things in FP16 and then refining up to FP64, generation over generation, that performance is improving greatly for mixed precision. But there's one other to think about, and that is, what if we don't want to do FP16 and refine up? What if we actually want to do our work in a higher precision, like an FP32 and an FP64? Is there anything we can do there to make those go faster? And the answer to that is some of the work that's been done around emulated gems, right? Using emulation to use those lower precision units to construct the full FP64 or FP32 precision, but just in a way that is not using one piece of hardware, but it's using many pieces of hardware together. And we can see definite benefits from this approach. One of the nice things about it is actually about flexibility. If you look to the performance piece here, relative to a native implementation, on Blackwell we're seeing more than 2.5x performance and performance per watt using an emulation method for FP64 DGEMs. But if you happen to be an application that needs a little bit less in those DGEMs, you actually have opportunity to capture even more performance, right? So this is actually tunable. It goes the other way too. If you need more than 64-bit precision, you can actually tune it the other direction as well and have a direct trade-off between performance and the accuracy of your results. And developing this capability has happened, again, not just with us. It's been done with partners. And we've been working with people across the world, experts in numerical computing and scientific computing, for them to test it, for them to find the benefits of it, and for them to try and break it, right? For example, we have a specific interaction with Jim Demmel at UC Berkeley, who is a widely recognized numerical precision expert, and we basically asked him, can you tell us how to break these? He said, yes, I can. Here's some tests. And so we have then since taken those tests and built libraries that can tolerate and know when those cases would happen, avoid them, and successfully use these methods in a way that's reliable. Okay? So these interactions have been key to helping us go from research paper on Haroon's desk to where we are today, which is a fully implemented version of these capabilities in the CUDA-X libraries. If you are on a CUDA 13 update 02 or later, you can use an environment variable to turn this on, and you can call dgem, and it will, on anything where it's beneficial, Blackwell and beyond, and it will use this method. It will give you the right answer. This is something we've, again, developed over time. The methods behind this, in terms of the protection methods that make it safe, you can read about. It was actually a paper published at this conference and was presented, I believe, yesterday. So as a result, we found ways on Blackwell to leverage those lower precision units in a way that was from a developer standpoint, very easy. It's just called dgem. You change a flag, you call dgem, you get more performance. Now, it's fairly narrow. It's just dgem. It's not vector, which is a different story, right? We're still doing that completely in native hardware. But it's a step in the direction that's both developer-friendly and gives more performance. In Rubin, which we recently announced, I do want to point out that we've actually posted on the spec sheet, here are numbers we expect to get with these methods. And as I mentioned earlier, we developed the software to learn how to build the hardware. There are actually hardware implementation details in Rubin intended to make this run faster and more efficiently. So again, it's this cycle of understand the software, understand the algorithms, make sure the hardware supports it well, right? So one last word on the landscape, right? We talked about simulation and AI becoming integrated. There is a third new emerging modality, which is, of course, quantum computing. And we are working with many people on quantum. Within the scientific domains, there's a lot of interest in figuring out how quantum computing and quantum algorithms can be used for scientific problems. And we think that enabling a future using quantum is going to be a heterogeneous future. It's going to be using classical computing and quantum computing together. There's many reasons for that. I'm sure you've heard them many times at conferences like this. What we are trying to do at NVIDIA is try to make sure that this is as smooth as possible, that there are defined interfaces for connecting quantum computers with classical computers, that there are software methods and libraries for simulating and advancing these computers, these hybrid computers, as well as the development of quantum computers themselves. And just as an example, here's some work our partners have done, a couple of our partners have done, on our systems, such as at Jülich, a very large state vector calculation of 50 qubits that was performed this past year on their new Grace Hopper system. And then on the right is a really fascinating simulation done at NERSC, where they actually simulated the electrical properties of an entire QPU on Perlmutter at pretty tiny micron level details. This is, sort of watching a quantum computer breathe, right? What I find really fascinating about these two is that on the left, you really have an early version of quantum EDA in both of them, right? You have sort of quantum logic design on the left, and you have kind of quantum spice simulation on the right. Because as the quantum ecosystem evolves, eventually they're going to want to have better design tools like the silicon and classical computing has. So steps are being taken in that regard that not only show interesting results, but eventually are going to enable new developments in computing. Okay. So altogether, we're working forward on building systems. We're building these systems to address not just one pillar. We're building it to address all three. And in particular, we're working on the hybridization and the full integration of simulation and AI, and we're doing it with partners across the board in hardware and in software and in this ecosystem. So we're very proud to be partnering as part of this project. You will hear more from all of us over the coming years as we make our developments, and as we learn things, we hope to be able to share them with you. Thank you very much.